Dear students, welcome to the interaction session of our course Aircraft Propulsion. In the last interaction session, we had covered the part which was initial, which was related to the Brayton cycle and different attachments of Brayton cycle. Then different versions of performance with those attachments and how we are going to actually work with it. That's what we had seen. And then it comes to the actual aircraft engines, which is what we are covering in latter part, and then components of actual aircraft engine, which are compressors and turbines. So these two things are, rather these three things are getting covered in latter part, and if you have any queries and any questions related with that, we are discussing. Although I have got certain questions from some students which I will be answering. You may also keep other queries posted here so that I will try my best to answer your queries. So let us go to the first question. Okay, so the first question states that why are we considering static properties at inlet and outlet of the engine, and why not total properties are considered? So we can consider static properties at inlet and outlet, that is not a problem. But first we have to understand why we are considering static or total properties. Basically, whole problem of aircraft engines can be completely solved with static properties. We, frankly speaking, would not need total properties if we assume certain things. And then we account certain losses in that. So as what we consider that in the combustion chamber we have constant pressure. So that pressure is static pressure, which is assumed to be constant. But in the combustion chamber, in the process of combustion, there are losses which don't get accounted if we use static pressure or static properties. So to account that, the loss in the combustion chamber. Further, we have also seen that there is an arrangement of heat exchanger. So in the process of heat exchanger also, there would be loss of total pressure. So in the processes of heat transfer, the losses should be accounted, and for those losses to get accounted, we consider total properties. And by considering those, we would have solved certain examples. The total pressure loss in the combustion chamber is 2%, total pressure loss in the combustion chamber is 3%. So these things, when we account, we are basically making more and more precise estimates. Just by considering static properties, we are correct to the certain extent, but if we want to be more accurate, we go towards total property. So in all, it's not compulsory for us to go ahead with static total properties. We can use static properties as well. For you, from the perspective of example, if total properties are given, you would go ahead with total properties. Or other hint is, if total pressure loss is mentioned in the combustion chamber, then we have to go and solve the example with total properties. That time we cannot solve the example with static properties. But if combustion chamber pressure loss is not given or total conditions are not given, in these both cases, we can go ahead and solve the example with static properties. Okay, so this is the answer for the first question. Second question, it's similar. In some examples we consider stagnation properties, and some example we consider real properties. So how can we decide? So this question is same. We have to first understand, again I am telling the same fact, we have to first understand why we are taking total properties and why we should not take sometimes static properties. Once this concept is clear with us, we would understand then when to use what. So I will again repeat that if combustion chamber pressure loss or pressure loss in the heat exchanger, if these things are given, then this remains a hint for us that we have to use total properties for solving the question. Unless otherwise, it might be written in the example explicitly that solve the example with total properties. So this is how we would proceed. Then we have one more question. In axial flow compressor or turbine, we have stator and rotor for one stage. Generally, stator is fixed, not rotating. So it has no blade velocity. But the velocity triangle for stator, we drew blade velocity u. What is the reason? Actually, this is not proper. Whenever velocity triangles are drawn, we are always drawing the velocity triangles in the mid-height plane of the rotating blade. So it is always stated multiple times in the class that we are using assumption that we are working at the mid-height of the rotating blade. So all the velocity triangles we are working with mid-height of the blade. Secondly, whenever we are saying velocity triangle, we are talking about three velocities. So one is absolute velocity of the fluid, one is velocity of the blade. So there is relative velocity of the fluid which is present for entering into the blade or leaving out of the blade. So there are three velocities. But when we talk about stator, there is no rotating velocity of the blade. So there is no relative velocity. So we have only one velocity. So we are principally not having three sides of a triangle. We have only one side. So we are not drawing any velocity triangle for stator. We are just drawing velocity triangle for the rotating component, which is rotor. Okay, so we'll go to the next question. How theta beta Mach number relations are calculated without considering the chart regarding those? Which mathematical method researchers use? This was the question. I'm not exactly understanding in what perspective this student is asking this question, but there are two theta beta Mach number kind of cases which I would tell. One theta beta Mach number case is there in gas dynamics, and where we say that theta is shock angle, theta is flow deflection angle, beta is shock angle, and m is Mach number. So this theta beta and Mach number, they are interrelated with each other, and for which there is a correlation, there is an equation. So if you know Mach number and if you know flow deflection angle, then you can find out beta, or if you know beta and theta, you can find out Mach number. So for this correlation itself, or for this expression itself, there are charts what the student is currently indicating. So either we have to go with the chart, or we have to simply use the mathematical relation and find out. Knowing the two quantities, we can find out the third quantity. But this is towards compressible flows or gas dynamics, and in our complete course we are not considering flow to be that much problematic, where we are having shocks and all. So these are always neglected. In the examples also you would see that we are saying that the flow is entered smoothly into the blades. So there is no shock present for us. If at all shock would be present, then we would have to account the loss of total pressure in the presence of shock, and then that would get further reduced efficiency for the turbines or compressors. So this is the one theta beta Mach number kind of case. Other what I am understanding is for present velocity triangles, we are using beta as the angle for relative velocity and theta as the angle for absolute velocity. Then those kind of angles which we are actually knowing, that those get evolved. So one is the theta, which is flow velocity angle, that actually depends upon our setting. We set the stator blades, or we set the nozzle at certain angle to the blades, so that theta gets known to us. And then beta actually gets evolved by measuring u velocity of the blade and knowing the v velocity, absolute velocity of the fluid, we can find out beta. So that is how here theta and beta can be measured, and Mach number will get calculated isolatedly in this case where we have to use relation V upon A, where V is velocity, absolute velocity of the fluid, and A is speed of sound in the medium in which we are traveling. So these are the two theta b times. Student may opt accordingly. So then we will move ahead with the next question. First slide.
All the answer. Questions are what questions are answered?
Okay, so there is one question related to assignment 8 and 9. Some options also didn't match. We will work out. We will let you know about assignment 8 and 9. What was the issue? There was one issue about uploading the assignment. I know it. So we will resolve that issue. Thanks for indicating it. There is one question on what is the difference between governing pressure ratio and actual pressure ratio. That is, okay, and optimum pressure ratio. Okay, so governing pressure ratio and actual pressure ratio, they are same. That is not different. So they are different words what we use in the examples. So governing, and most of the times these pressure ratio are related with compressor. So what we would have seen that due to combustion chamber pressure loss, we get the lower total pressure at the entry to the turbine than the total pressure at the exit of the compressor. So turbine pressure ratio remains to be lower than the compressor pressure ratio. So governing pressure ratio or actual pressure ratio, whenever we mean, we practically mean for the pressure ratio for the compressor, which remains to be the higher in the complete circuit. Further, optimum pressure ratio is different. Optimum pressure ratio gets evolved. Actual or governing pressure ratios are the working pressure ratios for the cycle. And for given conditions of maximum temperature, for given conditions of the inlet to the compressor, we have to find out what is the optimum pressure ratio for which we get certain conditions satisfied. What is that certain condition? We generally have resolved it for maximum network output. So maximum network output, when we achieve corresponding pressure ratio, is called as optimum pressure ratio. So optimum pressure ratio is different. It's not visible in the cycle. But in the example, it might be said that the cycle works with optimum pressure ratio. So that time we would have to find out the optimum pressure ratio, and optimum pressure ratio remains the governing pressure ratio for the cycle. Okay, so these are the answers, multiple answers or multiple understandings for the concept of actual or governing pressure ratio. Yes, liquid cooling is used, may not be in the aircraft propulsion, but in the electricity generation, liquid cooling of the turbine, or maybe ejection cooling or transpiration cooling is used for the turbine blade cooling. So then there is a question, what is RAM efficiency? RAM efficiency, if you go back, we have defined it for the intake of the engine, or we also use it for the ramjet or scramjet, where intake intake's job is to compress the fluid instead of actual rotating device, which is compressor. So we define it as the performance parameter of the intake. So ram efficiency is how efficiently your intake is compressing the fluid so that there is no loss in the total pressure. So less and less loss in the total pressure means higher and higher will be the ram efficiency. This is how we can understand the concept of ram efficiency. Then what is cascade? Cascade is the flow between the blades or flow passage through the blades, and so this is what we are using when we are working with the cascade kind of tunnels or cascade kind of operations, where we want to see what is the flow pattern when there are multiple blades, multiple stacks are placed, and then how flow would go from stator to rotor and rotor to again stator. So these kind of things are between two blades of stator. Okay, so we will go to next question. Okay. How can decrease the blade height in downstream flow direction? Okay, I mean the question would be why the blade height decreases in downstream direction, and this is more true for compressor. So for compressor, we are getting that the blade height decreases in the axial direction. We can understand this fact that in the compressor or turbine, we have understood one fact that the axial velocity doesn't change. So axial velocity doesn't change in the compressor or turbine. Further, in the compressor, what is happening? Density is increasing. So density is increasing. So these are the steady flow machines where mass flow rate should remain constant. So if axial velocity is remaining constant and density is increasing, so area has to decrease so that mass flow rate remains constant. So keeping this point in mind, we have to decrease the height of the blade in the compressor, and contrarily we have to increase height of the blade in the turbine such that mass flow rate remains constant. Yes, the pattern stated is correct. 75 25, 75 for NSEM and then 25 for the, at this moment this is in any update would be let you known to you, but to us this is what the present final exam statistics or final grading statistics. Okay, can you explain more on choking? So choking is a phenomena here in case of gas dynamics where mass flow rate doesn't change with certain changes in the flow property. So what is that? We will try to understand it more. If there is a duct and in that duct there is one inlet and one outlet, and then the flow in a duct in a duct will be governed by the pressure difference between inlet and outlet. So let us consider that inlet is static, inlet is zero velocity, so there is a total condition available in the inlet, and outlet is having certain pressure. So to start with, if both the pressures are same, there is no flow which is possible. Now if we keep on decreasing the outlet pressure, which is a static pressure, so due to the pressure difference between the inlet and outlet, there will be flow. And if we keep on decreasing the outlet pressure, the mass flow rate will increase. More and more mass will come out from the inlet and it will go towards the outlet. But at a certain point in the exit pressure, whatever decrement in exit pressure you do, there will not be any change in the mass flow rate. Mass flow rate remains constant. And so that condition where mass flow rate doesn't change with change in outlet pressure for given inlet conditions is called as choking. And what is the indication of choking? Minimum area would achieve Mach number 1. So this is the indication, this is the characteristic of choking, that the minimum cross section area achieves Mach number 1 in due course of time when we are decreasing the pressure. So this is what we mean by choking. And in the case of choking, we use this choking in many aspects, either to let the flow go from subsonic to supersonic, or to achieve just sonic state if it is of our interest. So these are the questions. What is subsonic supersonic intake? Scramjet means supersonic intake, and other engines whatever we are considering, turbojet, turbofan, they are subsonic intake. Means the intake flow remains subsonic, means the velocity at the inlet to the compressor or velocity at the entry to the engine completely is subsonic. Subsonic means the velocity is lower than the speed of sound, and we know speed of sound, if the flow has at a location temperature T, then under root gamma RT is the speed of sound at that location, and if V is the velocity at that location, then V by A is Mach number, and if this Mach number everywhere is subsonic, which is less than 1, then we call it as subsonic flow, and if this Mach number is more than 1, we call the flow to be supersonic. So this is how we are defining how the intake is receiving the flow. If intake is receiving flow to be having velocity lower than speed of sound, it is subsonic, and if the flow is having velocity more than speed of sound, then it is supersonic. Velocity triangle for wheel. Velocity triangle in general will not be a different concept wherever we work. In steam turbine, in gas turbine, in water wheels, everywhere velocity triangle would be same. There as well you will have absolute velocity, there as well you will have wheel velocity, and then you have to draw this absolute velocity in its direction, and then in the tangential direction you have to draw the blade velocity, and then your relative velocity will automatically get drawn. Okay, what types of vanes are used in the stator of the axial compressor? Axial compressor by default would have degree of reaction, so which is not basically impulse type of, so it is reaction type of compressors. And so in most common practice we can assume that the axial compressor rotor and stator blades are similar. So these are the vanes basically in case of axial flow compressors. Don't worry, if at all you missed, this is a live session, you will always get back with the answers whenever you want, but I meant while telling that we never draw velocity triangle for a stator. We draw always velocity triangle for rotor, and always in the rotor also, for the sake of simplicity, we always draw velocity at the mid-plane height and not anywhere. Okay, I will see into the assignment 11, question 11 of assignment 12. I'll get back. Question types will be similar. Whatever you are getting in your assignments, the same type of question would come in the examination also. So don't have to worry too much. If you would have practiced assignment well, then exam is similar. Yes, we will try for assignment 9. If there is no issue from uploading perspective, we will try to put the assignment number 9. We will come back to you in that case. So please let us know if there are any questions. First slide. Okay, so regarding the frame of reference, actually the forces experienced would not have impact on our assumption. So we can go ahead with the we should remain consistent with our assumption. If we are consistent in our assumption, then accordingly we will proceed. So I will not state that we are using particular concept over here. You can rederive your facts, whatever frame of reference you want, and you can get accordingly the formulation for that. So we will remain here to be what state we have and the way we have rather derived. Manufacturing details of compressor. Frankly speaking, these are the things which one can get from particular uh, components or particular companies and their manuals and then their websites. So these are less stated in the books, but if I have availability of those, I will pass on to you. No, don't worry. Component matching examples we will not be working with. That is not. Our examples will be on basically cycles. In the cycle, simple cycle, cycle with heat exchanger, cycle with reheater, combination of heat exchanger, reheater, and also maybe intercooler. So these are one type of examples. Other type of examples what we have seen are about the engines. So engines are there, turbofan, turbojet and turbo fan kind of engines. And then third example set will be on compressor and turbine. So these are the examples, and then objective questions, objective questions will be asked in the theoretical part of the syllabus. So this will be the composition of the exam. Yes, all questions will be MCQ types. Okay, so the question answer is yes. We are using inertial frame of reference. It's not non-inertial. All questions will be MCQs type. You'll have to solve and choose one correct answer given among them. The data will be available with you. In case of compressor stall, what would happen is now in case of compressor stall, the angle, flow deflection angle becomes so large that the flow gets separated in the case of over the compressor blades, and then compressor would not operate to the extent what is our requirement in case of compressor stall. And what practically we mean in case of surge is the flow. These are the machines which are non-positive displacement machines. So in case of positive displacement machines, flow comes from the inlet and goes from the outlet. So it's not possible that flow can come from the outlet and goes out from the inlet. But in the case of surge, it can happen that the flow can come from the outlet and goes towards the inlet. So surge and stall are these kind of situations where they are linked and they are happening in the compressors. Let us work on examination day. On the exam, we will not. The most of the questions are answered regarding the examination, and we will keep ourselves towards the aircraft propulsion, and we will ask the questions and answers related to aircraft propulsion. Although I am answering this question that whether steam remains an ideal gas to find critical pressure in the converging diverging nozzle of compressible flow and critical pressure. So although you are saying that it is assumption, so you should proceed with your assumption and find out your estimates. So that's what I can say at this moment. Obviously rocket nozzles are seen by us, we can see from outside. They are bell-shaped nozzles. So a contoured nozzle or bell-shaped nozzles are used in the rocket. You can see that at the bottom part of the complete launch vehicle you see rockets, and the shape of the nozzle is also a bit explicit for us. Yes, we will work on assignment solution and we will send back to you. Thank you. Okay, so since we have no questions, we will proceed herewith for the exam. So keep working hard, keep safe, keep yourself safe, keep yourself healthy. Okay, choice of blade depends upon our increment in compressor and number of stages what we are planning for. So basically it is governed by the amount of pressure rise which we are interested in. So that is how we are going to define the or to choose the blade profile. I did not get the question. What pressure ratio will root in double compressor? Okay, so rest of the questions. Okay. Turbofan engines, I think it is very basic related to the engines. We know that turbofans are having lesser noise in comparison with turbojet, and turbofan are more economical in case of, yes, in comparison with turbojet. So most of the commercial airlines use turbofan engines instead of turbojet engines. So this fact already we have seen in the class. Advanced course, with this course will be special course on compressor or special course on turbine, where we are not going to go in the perspective what we are seeing over here. We are looking from the gross perspective completely. We are not going in minor details. And advanced course will be special course on each compressor or maybe a turbine. So we will take rest of the questions in our forum. So thank you very much for your interaction. We will see you in the exam, and be healthy, be safe, take care. Thank you. Thank you very much.